on the G-Shock sensor. We are sponsored by Instrumented Sensor Technologies, which are located in Okemos, Michigan. Our facilitator is Dr. Radha, and our sponsor contact is Greg Koschel. I'm DJ Kohler.
Shuhan Chen. Dan Svoboda. Corey Fox.
Tim Carroll. And Carl Anderson.
So a little overview about what we're going to talk about is the introduction, some design specifications given to us by our sponsor, some possible design solutions, talk about risk analysis and budget. So basically what we're going to be doing is we're going to be developing a device that will monitor the acceleration experienced by that device. We're going to be doing that by the use of an accelerometer. Based on what our sponsor told us, he wants it to work in a single axis. Most accelerometers nowadays work in 3-axis, so they work in the X, Y, and Z coordinates. Ours will just work in just the X coordinate. In addition, we'll have 2 modes, real-time mode and a peak hold mode. So a little about the operating modes that we have. In the real-time mode, it's going to display a maximum G-force reading over a 15-second window. So the clock is going to count the 15 seconds, then over that time, the acceleration experienced by that will hold the maximum value just for that 15 seconds. In addition, it's also going to show the RMS value over that 15-second period. In the peak hold mode, we're going to have display the maximum value that the device experiences over the time when the device is turned on. So this will mainly be used for shipping purposes, so over long distances of 30 days or something like that. While the device is on, it will hold the maximum value, and it will also display the date and time that that value is stored at. In addition to that, we'll have a reset button, which will be able to reset that time or that maximum value. Possible applications for our device would be simple laboratory measurements, in-plant machinery monitoring, shipping and transportation. That's really our main focus. That's kind of what IST already does at their company. Size should be third of a cell phone, so you can kind of slap it on the side of a box, and then once we assemble all of our parts, it should cost about $10 just to put it together.
So a little bit background about the accelerometer. As of today, the existing usage of the accelerometer is in vehicle acceleration and vibration monitoring when developing a car. And also in biology study, the body acceleration is monitored by the accelerometer. And also when monitoring the machine healthy and the structural healthy, it's used a accelerometer as the sensor to sensing the health. And also the step counter is driven by the accelerometer. Also our smartphone, the way the smartphone knows the orientation of the screen is driven by accelerometer. Also the camera image stabilizing is driven by accelerometer. And for the last fall, there's another team that was sponsored by the Instrument Sensor Technology, was doing a 3-axis cutoff sensor, and they will have like a preset value for the 3-axis accelerometer. Once the accelerometer meets that value, it will just cut off the relay, and it's like a safety switch. However, our team is actually using a 1-axis accelerometer, and we'll do like data processing in between. We'll have like peak code and RMS calculation. So we'll have like more work involved versus theirs. A little bit background about the accelerometer. The basic principle of the accelerometer is the mass in the middle, and it have like spring loaded on both sides. So when it's balanced, it will just stay in the middle, and when the whole thing moves, the mass will shift, and then we will have like either current or voltage output to measure. And next slide, please. The accelerometer that we are going to use is a MEMS device, which is a micro electrical mechanical system. After a certain kind of chemical reaction on the silicon chip, it will create different fingers, and it will be like capacitant fingers. Those is the fixed plate, and that will, after we apply voltage on that, we'll have capacitance, and we'll have moving plates too, actually acting in the middle of the capacitant plates, and that will change the capacitance, and then the voltage outputs were actually acting as the G value.
All right, I'm going to talk a little bit about the design parameters that we had to consider when approaching this project. So our sponsor has given us several design specifications that the G meter will have to perform up to. Some of the measurement capabilities that it must have, it has to be able to measure a minimum of 17 Gs in either direction along the axis of measurement. Must have a resolution of 0.04 Gs, meaning that it can detect a minimum change in acceleration of 0.04 G forces. It has to have an accuracy of plus or minus 3%, meaning that the actual reading that you're getting from the meter is within 3% of the actual applied acceleration. The measurement rate must be able to take a maximum of 1,000 measurements per second, so 1 kilohertz max, but the measurement rate will be selectable by the user. Finally, it must perform its measurements over 15-second sliding time windows. So it'll measure the maximum G and RMS G value over 15 seconds and then update the display. Some other features that the device must have, obviously you must be able to select between the real-time and peak hold mode, hold modes that EJ described. It must output the G value and the time and date also to an LCD liquid crystal display. The device must have a battery life of at least 30 days on 2 AA batteries. This is necessary because when used in the peak hold mode, it must be able to hang on to the peak G value and hold on to that value over a long period of time. And finally, the size, as EJ also mentioned, should be comparable to that of a cell phone. We just want to keep it as small as possible. So when looking at these parameters, we split them into different specifications that we thought were critical to coming up with a successful design. We decided that all the measurement capabilities we would be able to hit, and there wasn't much trade-off among the different measurement specifications. It obviously must be able to operate in both modes, as our sponsor has requested, and the other critical item was the battery life. It must be able to last for at least a month on 2 AA batteries in order to operate properly. Some of the design parameters that we were more flexible on were the size of the device. We were sort of given a rough guideline, but our sponsors mainly concerned with the functionality. If they decide to put the device into production, they would try to optimize the size. And the cost, we were given a target of around $10 for $10 of parts cost when bought in quantities of 500 or more. That's sort of hard for us to estimate just doing a prototype, so this is sort of just a rough guideline for us.
So because Instrument Sensor Technologies provided us with a very rigid and complete set of design guidelines, many of which Carl just discussed, a lot of our proposed design solutions had highly similar high-level hardware topology to the diagram you see here. And a lot of the design decisions that we've made up to this point have involved selection of vital components like a microcontroller and LCD, and then either including or omitting a lot of non-vital components. Some of them that made the final design were status LEDs and momentary switches. So as you can see, at the heart of our device, we have a microcontroller. It receives data from an accelerometer. It does a lot of internal processing and software, and when it's in the peak hold mode, it stores values in its own memory. And then it outputs those values to the LCD through a Hitachi display drive. It also uses LEDs for status, and it uses momentary switches to take in input about scrolling on the screen and setting the mode and setting the time. It runs out 2 AA batteries, and we're using a 5-volt DC to DC step-up. So at the heart of our design, we selected as our microcontroller the TI MSP430 2553. The thing that really drew us to this microcontroller over competing models by companies like Atmel was the fact that it's highly low power. As you can see, it can run on half microamp in standby mode while still maintaining a clock signal. And we're going to use this to so that the user doesn't have to reset the time after turning the device off and back on again, which is important because our sponsor wants us to run for over a month, 2 AA batteries. We also like that it has 16 bits, or yeah, 16 I/O pins. There's analog and digital. We're using the digital to drive our LCD, our LEDs, and to take inputs from our buttons, and then we're using our analog pins in conjunction with a 10-bit onboard analog to digital converter to take input from our analog accelerometer, which we're getting from Freescale. Shuhan already discussed a little bit about the operation of it. It's basically a 3-plate capacitor with a mobile center plate, and this produces a voltage swing. There's internal circuitry that amplifies that voltage and gives us a fully linear output. So between G's and volts, it's a fully linear conversion, which is really nice because then in our software and our microcontroller, it's a simple matter of scale and offset in order to convert that voltage that comes in from the analog digital converter into a G reading to be calculated and put on the screen. For our LCD, we're using a Microtips 8x2 display. The main design parameter that motivated the selection of this display is the fact that it's highly interchangeable. It uses a Hitachi driver. It's actually a Samsung driver, this one, but Hitachi developed it. And it's a standard protocol that's interchangeable with a lot of other LCDs. Carl mentioned briefly that our sponsor might want this device to be scalable. He mentioned a watch-sized device or a larger device. And so the compatibility of this driver allows us to sub in a larger LCD or an LCD with a backlight or even an OLED backlight or OLED display that uses this driver. So that's very nice for us.
Right. We figured out that the final G meter could have 4 main risks. We ended up having 2 low and 2 high risks. The first risk is a defective microcontroller. This would be a high risk because we could have a short circuit. You'd have to send the product back and have it fixed. No display on LCD. As we keep mentioning, we have a 30-day window. So if it's past 30 days, if anything's wrong with the screen, it's probably because it has low battery. So it's a low risk, easily fixed. We have excessive current. Since we are using a step-up converter, if we do not put this together right, we could have anywhere between 50 and 100 milliamps that we don't want, which, as we all know, could be dangerous. Could actually drain the battery faster or even hurt any other circuitry. And we have inaccurate measurements. Like EJ said, we have single axis. If you want to measure the x-axis, you have to make sure that the meter that you place is in that correct axis. If you want to measure all 3, you need to have 3 meters. If you were to place it somewhere on an angle between the X and the Y, you would not be able to get clear measurements, so usually it's a user error, so that's pretty low. For budget, like every other group, we have $500, but we decided to focus on the $10 per unit price. They want us to be $10 if we were to make 500 or more units. As you can see, we're about $10. We're breaking up into 3 main parts: the accelerometer, the microcontroller, and the LCD screen. The PCB board and all that stuff, he does not want in the final budget because they'll end up designing their own at the end, and he wants to make mass quantities, possibly sell these on the market. And the reason why it's a single axis is because he can sell 3 times more per shipping container to measure all the axes. But for 500, the prices that we pay are a little bit more than this because we're only buying 1 or 2. But when you buy 500 of each of them, they end up being about $10.
All right, I'm going to talk about the project management part. These are just our non-technical positions. Carl and Dan are the presentation prep. Tim is the document prep. Shuhan is the webmaster. I'm the manager, and EJ is the lab coordinator. So a little bit of our technical positions. We chose these based on our abilities and what we wanted to do. Carl is going to be the data acquisitions manager, which means that he is going to be in charge of getting data from the accelerometer and converting it into something that we can use, programming the microcontroller to do that. Tim is going to be the power systems specialist, which means he's going to be in charge of designing the circuitry to get power from our batteries and supply it to our microcontroller, LCD screen, and accelerometer. Shuhan is going to be the product assessment and validation officer, which means that he is going to be in charge of taking the test data and making sure that it aligns with what the sponsor wants for our specs. I'm going to be the testing technician, which means I'm going to go to IST and I'm going to use their testing equipment and perform the test. EJ is going to be the assembly associate. He's going to be in charge of designing the encasement for our device, and he's going to be in charge of putting it all together. And Dan is going to be the display management, which means that he is going to be in charge of programming the microcontroller to output to the LCD display exactly what the sponsor wants. So, some of our resources and facilities. We're going to need the ECE 480 lab for the testing equipment they have, such as the power supplies. We're going to need IST for the G-force testing equipment. They have calibrated equipment, which is going to help us calibrate our G meter. Our device components, these are just the four main ones. And the software we're going to need is TI Code Composer. That is going to allow us to interface with our microcontroller. And we're going to use Eagle to design our PCB. So this is just our deliverable schedule. I'm not going to go into detail about that. But then this is our technical schedule. As you can see, the majority of our time is going to be spent programming. That'll allow us, if we get done at the right time, that'll allow us plenty of time at the end of our project to have plenty of time to make final adjustments and optimize our design. So in summary, we talked about IST, what they want from us. We talked about the functionality of accelerometers, evaluation of our design parameters, final design decisions, how we're going to spend our money, and how we're going to allocate our time. Thank you. Are there any questions?
Thank you. Are there questions?
Is the 15-second window just an arbitrary number?
Yeah, that was just given to us by our sponsor. That's what he wants.
Okay.
Just to help us calculate the RMS.
How will you guys be kind of like applying this unit onto a box? Like how will it be attached to it? Is it like?
It's going to be inside of an encasement.
I mean, it wasn't really specified to us. That's sort of not, we're not really designed for that.
Well, right now they do like shipments overseas, so they have larger devices they ship on the back of those giant freighter boxes. But right now this one's for like commercial packaging, so if we were to go from here to Alaska or something like that, so it's got to be smaller. And it'll either be on the outside or inside on the actual product.
So you guys mentioned that if you made this with the one axis, their end goal was to sell it possibly commercially. So do you guys have to take into consideration like existing patents or if it's possibly patentable, what you guys are making?
I mean, I guess we haven't thought of that, but
We're just designing with the
What I want to
sponsor.
say. Okay.
Is it a requirement to put the LCD on every single accelerometer? Because I'm thinking you could cut the price in half if you had a data reading unit and then you just connected it up to each module when you wanted to read the data.
That kind of makes sense, but our sponsor, I think, he requested a very compact, robust device. I think it's because they're really interested in that one moment in time when the device fell off. The shipping container that had 10 Maseratis in it fell off the cargo ship. And so he wants something that's compact and that's robust to cross-examination if it's used for liability or something like that.
Right.
yeah.
So it looks like the toughest part of this is the power requirement, 2 AA batteries for 30 days. This basically has to be on all the time.
Well, the LCD takes up the majority of our power, so we're going to have that go on the sleep timer so that it shuts off after about probably 15, 20 seconds and then press the button and it comes back on.
Yeah.
That'll save us a lot of power.
And also the microcontroller has some low power modes, that can run at very low power. Like I saw a video on YouTube of some guy was running the microcontroller just on a charged up capacitor for like 3 weeks. So it was.
So what's the plan for doing the power testing? I guess you won't have it done probably 30 days before.
Yeah, I mean, I guess we could just try to monitor the current somehow and try to extrapolate from there on this.
Other questions? If not, thank you.